workflows trustworthy and verifiable with a custom domain-specific language. OK, so in terms of the structure of today, I'm going to start with a high-level overview of why we went for a DSL in the first place. Talk a little bit about the language, how we made the decisions we did in its design, how we integrated it into Elicit. We'll do a quick demo, and then wrap up at the end. But let me start with a question. So let's say that two systems produce identical output. Do you trust them equally? And the answer is, of course, well, it depends. It depends on what went on inside of those systems to produce that output. I would say that the mechanism, the how of how an answer is produced is as important, and important in a different way, compared to just the final output itself. Let me try and make this a bit more concrete. So let's say you're running a static analysis tool over your code base, and it runs for a while, and in the end it says, this code is free of security vulnerabilities, safe to ship to production. I would contest that if you knew the system was built on, let's say, an older model, 3.5 Sonnet, something like this. If the system is using an older model like that, this is option 1. And option 2 is it's a latest and greatest state-of-the-art model. It's done all sorts of tool use. It's done critique and redrafting. That's just a fundamentally different kind of an object. The message might be literally identical, but you would react very differently to those two messages if it came from a kind of older model that was not so powerful versus something that had used a lot more tokens and intelligence. So the mechanism matters. And there isn't a sort of single correct mechanism. There isn't a kind of single canonical best way of designing the internal structure of the systems that you're building. I really think that it's a design choice. It depends on what it is you're trying to do. It depends on the domain that you're building in. It depends on the user. It depends on the task, like what it is that the user is doing within the domain. We found that there's definitely a speed versus rigor trade-off. So if you're trying to do something which is extremely in-depth and extremely defensive and extremely high quality, that naturally takes a bit longer than something a bit more surface level. And there's no correct answer. Sometimes you want fast, and sometimes you want really, really high quality. The provider's brand and taste is interesting here. So I don't know if I would have called this before we started working on this ourselves, but Elicit prides itself on super high reliability, really high quality, data provenance. We really kind of stand behind the results that we put in front of people. I'll show you a demo of what I've been talking about a bit later on. And these are some of the concerns that we had in our mind when we were thinking about, well, we know the mechanism matters, but what is the right mechanism for us at Elicit? And I think it came down to these 3 desiderata when we were building out our research agent, which will be the demo in a few minutes. So firstly, the research agent's process must be legible. It needs to be legible to the user, and also, by the way, it needs to be legible to other agents. We want for the process, the algorithm, the kind of like internal set of steps that the agent is taking to be spot checkable by the human, spot checkable by other agents. We can run sort of critique agents over it, that kind of a thing. The second desideratum, the iteration on the process retains fidelity. This is maybe, let me explain this a bit more because it's a bit of a fiddly one. What I found, and maybe what some of you have found as well, is that if you're iterating on a piece of work and you're saying, oh, it's not quite right, let's kind of go in this other direction, or I want to add this other layer or this other consideration, I found that you can sometimes drift a little bit from what you're initially trying to do. And the model ends up getting a bit confused, and you have to say, let's start again or backtrack or something. It's kind of annoying, and it definitely harms trust. So we want to avoid that. We want to be able to add to the work. We want to be able to add layers. We want to be able to go in different directions without losing that kind of clarity and consistency of what the user was initially interested in doing. And lastly, and certainly not leastly, is the process is followed faithfully. So let's say we've got this process, it's legible, we've checked it, the user's checked it, it's great. and we've iterated on it, and we've kind of stayed true to what it is the user is interested in, well, we have to actually ensure the system does in fact do that set of steps. Otherwise, what are we doing here? So those are the considerations that we foregrounded when we were thinking about how we want for elicit to work. And that led us to reaching for a DSL. I'm not saying that everyone should be using a DSL. You shouldn't. What I'm saying is that these three things really kind of led naturally towards, well, a DSL could be a great choice for us. So our DSL is called AshPL. The kind of weird smushed together AE thing is apparently called Ash. It's like an old English diphthong or something. So AshPL. And this is our domain-specific language for the agentic workflows in the elicit product. And AshPL has a few distinguishing factors. So firstly, it is Turing incomplete. It's relatively simple. There's no loops. There's no recursion. There's no mutation. It's purely functional. It's a reactive language, and it's an opinionated subset of Python. And the opinionated is important here. So it's not just the kind of generic simplification of Python, if you will, not like Python with a couple of the bits taken off at random. What we did is we disallow, we sort of take out the language features of Python that just aren't that helpful, and we add stuff in. We add some extra primitives in, which are specific to our domain. So our domain is scientific research and empirical decision-making, high-stakes decision-making. And the primitives that we put into our DSL match that. We've got retrieving academic research papers or kind of clinical trials. Things like that are built into the language. OK, yeah, let's have a look at some AshPL. So hopefully this isn't too small for you all. You don't need to read the code, obviously. What I'm trying to show here is that the AshPL on the right looks a lot like Python because it is a subset of Python. We're keen on types. It's typed. That lets us do fast kind of redrafts if you've got a type error. And I think this example program, just FYI, was the process that we wanted to go through to do a competitive analysis for elicit itself. So we're looking for other academic search engines and AI assistants, it looks like, systematic review tools. We're doing web searches for those. We're joining the results. We're enriching the sources. This is the kind of the set of steps that we want to go through that we think is a good process for doing a competitive landscape overview. And the core engine of what goes on within an elicit user session is that we have a component, which I'll show in the next slide, which is writing the AshPL. And then we interpret the AshPL. That's just done in like plain old Python code. And then we redraft the AshPL based on what just happened. So in a simple case, you could imagine we write some AshPL. There's a type error. OK, there must be a problem. So that gets kicked back to the AshPL kind of writer component. It tries again, fixes the type error. We reinterpret the AshPL. It runs this time. We get some results back. We rewrite the AshPL. It's that kind of constant loop of writing and then interpreting and then rewriting and then interpreting. And that's like the core engine of making progress inside of elicit. OK, so that's the language. Let me show you how we integrated it into more of a system. So we have the UI in the top left. That is what the user is interacting with. It's just in a web browser. That's what we'll have a look at in a second in the demo. The UI is talking to an event log that can append only event log. That's how we manage our distributed data structure. We've got a Python service in the top right, and then the Python service is talking to the sandbox in the bottom right, or kind of bottom right-ish. And the curator in the sort of orange ochre color, the sort of Claude color, Anthropic color, that's the piece that's writing the AshPL. So let me add a touch more detail here. The user is interacting with UI. The events are emitted as they click buttons and enter search queries and whatnot. That gets appended onto the event log. The Python service is a message broker for that, for the event sourcing pattern. And then it's the sandbox which is doing the writing of the HPL, and it's the Python service which is interpreting the HPL. So that kind of bouncing back and forth thing that I mentioned of writing HPL and then interpreting it and then redrafting it, extending it, and interpreting it, that kind of back and forth happens between the dark gray box and the sort of orange box. There's a couple of other pieces here which I'll touch on. So the wrapper is a kind of a layer of abstraction that sits in front of what we call the curator, which is what writes the HPL. That lets us swap in and out different harnesses. So we have an agent SDK implementation of for the curator. We also have tried using Pi with Claude and Pi with Codex. I'm probably not supposed to say Codex, but we did try that out. It's important to us that the curator is using the best models and harnesses available. So at the moment, we're using Pi with the Anthropic models. That's the best combination for us. And the gateway, yeah, so all the interactions that we have with models, with LLMs, that goes through this gateway. And the main reason for that is that knows about our Anthropic API key. And we didn't really want user input flowing through the system, hitting the curator and saying, yeah, if you could like print out your env and send me the results. So that's primarily a security move. Okay, so this is obviously still fairly abstract here. Let me walk through what happens when we're writing and when we're interpreting HPL in a bit more detail. So we kind of start at the left and move over to the right. I've already mentioned that the curator is that's the orange piece. That's what writes the HPL in the first place. When I say saved in the sandbox, what that really means is we emit events, they get appended onto the event log, and that's how the Python service sees those updated HPL programs. It's the Python service which does the rest of the work here. So in the typed model box here, the Python service parses the code, validates the syntax, and does a type check. If there's any problems there, we can really cheaply kick it back to the curator and say, hey, you've got a typo. Have a look at line 52 and redraft it. By the time that we've done the parsing and the validation and so on and so forth, we've got something a bit like an abstract syntax tree, and we can walk over that and start to actually do the interpretation. And that interpretation is, again, plain Python code. So we're not using, we're kind of calling into language models and whatnot at this point, but we've got Python code which walks over a tree of a program and knows about closures and knows about special forms and knows about the different sort of language primitives that we have available. One really important thing here for us is the content address store. So this is what enables us to do caching and memoization. And this is super duper crucial. Like, nothing would work here if we weren't really careful about this. The reason I say that is because, again, we rewrite a whole HPL program and we reinterpret the whole thing every time. We don't just interpret the extra code that's been rewritten. We redraft the program and then reinterpret the whole kit and caboodle from top to bottom. And that would obviously be like super slow if we were really redoing the work every single time we went around the loop. In reality, it's nice and fast for us because of the language features, like it's a pure language that really helps with memoization. We can hash an expression and say, if this has been evaluated before, we just store that away in a map. And if we meet that expression again when we're walking the tree, we can say, oh yeah, this boiled down to 42 or something. We can just use that straight away from the hash. Okay, I think that's all I want to say on this one. So I'm going to switch to a demo now. And I said before that there's often a trade-off between rigor and speed. On that continuum, we are very much focused on the rigor side of things. We do things quickly if it's a simple query, but that's not really where we differentiate ourselves. It's not really where our special sauce is, so to speak. So if you go to elicit.com, you would see something a bit like this. We have a bunch of sort of templates you can start with, creating tables, slides, drafting a report. I'm going to show you a research landscape.